Hello and welcome. Imagine for a moment looking up at the moon on a clear night. For thousands of years, humanity could only wonder, only dream about what it might be like to stand on that distant glowing sphere. It was a place of myth and mystery, forever out of reach, until one day it wasn't. This is the story of how that impossible dream became reality. This is the story of Project Apollo. What you're about to hear is perhaps the greatest technological adventure in human history, a story of breathtaking ambition, heartbreaking tragedy, brilliant ingenuity, and ultimately triumphant achievement. It's a story that unfolded not over centuries, but in a single, dizzying decade. A story that began with a president's bold challenge and ended with human footprints on another world. We'll explore everything: the political pressure of the Cold War, the technological breakthroughs, the courageous astronauts who risked everything, the brilliant engineers who solved impossible problems, the scientific discoveries that transformed our understanding of our place in the cosmos, and the lasting legacy that touches your life today in ways you might not even realize. So, settle in. We're about to embark on a journey together, a journey to the moon and back, and I promise you, by the time we're done, no stone will be left unturned. To truly understand Apollo, we need to step back in time to the late 1950s. The world was divided by the Cold War, a tense geopolitical struggle between the United States and the Soviet Union. This wasn't a shooting war, but a battle of ideologies, of systems, of ways of life. And a crucial battlefield in this conflict would be space. On October 4th, 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite. That simple beeping ball, barely the size of a beach ball, sent shock waves through the Western world. If the Soviets could put a satellite into space, they could likely deliver nuclear weapons across continents. American technological superiority, something the nation had taken for granted, was suddenly in question. The pressure intensified when on April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human in space, completing a single orbit of the Earth. Just days later, the United States suffered the humiliating Bay of Pigs fiasco in Cuba. For the new American president, John F. Kennedy, these events created a perfect storm of crisis and opportunity. Kennedy needed a way to demonstrate American technological prowess beyond doubt, to restore national prestige, and to prove the vitality of the free world. He turned to his vice president, Lyndon B. Johnson, asking him to identify a space achievement where America could decisively beat the Soviets. The options were narrowed down: putting a space station in orbit, sending a man around the moon, or landing a man on the moon. Johnson consulted with NASA officials, including its administrator James Webb and rocket pioneer Wernher von Braun. Their conclusion? A moon landing was the most ambitious, most achievable, and most definitive way to win the space race. And so, on May 25, 1961, just 20 days after American astronaut Alan Shepard became the first American in space on a 15-minute suborbital flight, President Kennedy stood before a joint session of Congress and issued a challenge that would define a decade. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind, or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. There it was. The goal was set. The clock was ticking. But in that moment, NASA had never sent an astronaut into orbit. No one knew how to navigate to the moon, how to land on it, how to survive on its surface, or how to return. they would have to invent almost everything from scratch. Kennedy's goal provided a clear, singular direction for NASA, but the agency needed to grow massively and quickly. In 1961, NASA was a relatively small organization. To achieve a moon landing before 1970, it would need to become something entirely different. One of the first major steps was the establishment of the Manned Spacecraft Center in Houston, Texas. This would be the home of the Astronaut Corps, the Mission Control Center, and the primary hub for designing and testing the spacecraft that would go to the moon. The site was chosen in 1961, and construction began soon after on a sprawling complex that would later be renamed the Johnson Space Center. Meanwhile, the Marshall Space Flight Center in Huntsville, Alabama, led by the brilliant German rocket scientist Wernher von Braun, was tasked with developing the massive Saturn rockets that would be needed to lift astronauts out of Earth's gravity and on their way to the moon. The scale of the workforce was staggering. At its peak, the Apollo program employed 400,000 people and required the support of over 20,000 industrial firms and universities. It was truly a national effort, a testament to what could be accomplished when a nation pooled its resources, its brainpower, and its will toward a common goal. But what exactly were they building? The initial concept for the Apollo spacecraft was a three-part vehicle, but the method for actually landing on the moon was still up for debate. Three main ideas were considered. The first was direct ascent. This involved a single enormous rocket that would launch from Earth, land on the moon, and then launch back off the moon to return to Earth. While conceptually simple, it would have required a rocket of almost unimaginable power, the proposed Nova rocket, which was beyond the technological capabilities of the time. The second was Earth Orbit Rendezvous. This would involve two separate launches. One would carry the spacecraft for the journey to the moon and back, and another would carry the fuel. The two would dock in Earth orbit, fuel up, and then head for the moon. This was more feasible than direct ascent, but still complex and required multiple perfect launches. The third, and the one ultimately selected in 1962, was the most daring and innovative, Lunar Orbit Rendezvous. Proposed by John Houbolt at NASA's Langley Research Center, this method involved a single Saturn V rocket launching a 50-ton spacecraft toward the moon. That spacecraft, however, wouldn't land on the moon itself. Instead, it would consist of two separate vehicles that would dock together: the Command Service Module, CSM, and the Lunar Module, LM. The CSM would remain in orbit around the moon with one astronaut aboard, while the other two astronauts would descend to the surface in the LM. After their moonwalk, they would blast off from the moon in the top half of the LM and rendezvous with the CSM in lunar orbit before discarding the LM and heading back to Earth. This method was brilliant because it saved an enormous amount of weight and fuel. They didn't have to land the heavy CSM on the moon or launch it back off the lunar surface, but it was also incredibly risky. Rendezvous and docking in the unforgiving void of lunar orbit, over 200,000 miles from Earth, had never been attempted. If the two spacecrafts failed to dock, the lunar astronauts would be stranded with no hope of rescue. It was a calculated gamble that would define the entire program. Let's take a closer look at the incredible machines that made the journey possible. The Apollo spacecraft was a three-part vehicle, each with a critical role to play. First, the Command Module, CM, built by North American Aviation. This was the astronauts' home during most of the journey. It was a conical capsule, about 11 feet tall and 13 feet in diameter at its base, roughly the size of a large car interior for 3 people. It contained the crew's couches, the main control panels, and the heat shield for re-entry into Earth's atmosphere. This was the only part of the entire stack that would return to Earth intact. Connected to the back of the command module was the service module, SM, also built by North American. This was a cylindrical section that contained the spacecraft's main engine, oxygen tanks, fuel cells for power, and other support systems. Together, the command and service modules were called the CSM. The service module provided all the propulsion, power, and life support for the journey to the moon and back, until it was jettisoned just before re-entry. And then there was the lunar module, LM, built by Grumman Aerospace. This was the most exotic-looking of the three. It was a spidery, fragile-looking vehicle designed to fly only in the vacuum of space. It had no aerodynamic shaping because it would never have to fly through an atmosphere. It was divided into two stages. The descent stage had the landing leg and a rocket engine to slow the craft down for a soft landing on the moon. It also carried the scientific experiments and, on later missions, the lunar roving vehicle. The ascent stage contained the cabin for two astronauts, its own rocket engine, and guidance systems to launch off the moon and rendezvous with the CSM. After the astronauts transferred back to the command module, the ascent stage was jettisoned and sent to crash into the moon. To launch this entire stack, NASA needed a rocket of unprecedented power. The answer was the Saturn V, standing 363 feet tall, about the height of a 36-story building. The Saturn V was a multi-stage behemoth that remains the most powerful rocket ever successfully flown. Its first stage, powered by 5 massive F1 engines, produced 7.5 million pounds of thrust, burning through tons of kerosene and liquid oxygen fuel in just 2.5 minutes to lift the rocket to an altitude of about 40 miles. The second stage would then fire to continue the journey into space, and the third stage would give the final push to send the Apollo spacecraft on its way to the moon. The Saturn V was an engineering masterpiece. Of the 13 Saturn V rockets launched, everyone was successful. With the technology taking shape, the schedule called for the first crewed Apollo flight, then known as AS-204, Apollo Saturn 204, to launch on February 21, 1967. The crew was selected: Command Pilot Virgil Gus Grissom, Senior Pilot Ed White, and Pilot Roger Chaffee. Grissom was one of the original Mercury 7. White was the first American to perform a spacewalk, and Chaffee was a talented rookie. They were a superb crew, ready to take America's next step toward the moon. On January 27, 1967, they were conducting a plugs-out test on the launch pad at Cape Kennedy, a full dress rehearsal with the spacecraft running on internal power, but without any fuel loaded. The massive Saturn IB rocket was not involved. It was just the Apollo command module on top of the rocket, sitting on Launch Complex 34. The test was plagued with problems, including static over the communications loop and a strange smell in the astronauts' oxygen supply. Then, at 6:31 p.m., a voice, believed to be Chaffee's, crackled over the comm. "Hey, we've got a fire in the cockpit." What happened next was horrifyingly swift. A spark from faulty wiring somewhere in the cabin, fed by the pure oxygen atmosphere at high pressure, ignited flammable materials inside. In the oxygen-rich environment, the fire spread with explosive force. The astronauts had no chance. The hatch, which opened inward and had a complex design of multiple layers, could not be opened quickly enough against the intense pressure that built up inside. In less than a minute, America's first 3 Apollo astronauts were dead. The nation was stunned. The program was halted. An extensive investigation was launched to determine the cause of the fire and to overhaul the spacecraft. The findings were brutal. The investigation uncovered a host of problems: flawed wiring, flammable materials used throughout the cabin, a hatch that was nearly impossible to open quickly, and a general culture at NASA and its contractors that, in the rush to meet Kennedy's deadline, had overlooked potential dangers in favor of meeting schedules. The spacecraft was completely redesigned. The pure oxygen atmosphere at launch was replaced with a safer oxygen-nitrogen mix. Flammable materials were removed and replaced with self-extinguishing alternatives. Wiring was overhauled, and perhaps most visibly, the complex multi-layer hatch was replaced with a single, unified hatch that could be opened outward quickly and easily in just a few seconds. The Apollo 1 fire was a profound tragedy. It cost the lives of 3 exceptional men and shook NASA to its core. But from this tragedy came a renewed commitment to safety. The changes made in the wake of the fire undoubtedly saved lives on later missions and ultimately made the successful moon landing possible. The mission, originally designated AS-204, was officially renamed Apollo 1 by NASA as a tribute to the crew. After the extensive redesign of the command module, NASA was ready to return to flight. The first Apollo missions would be uncrewed, designated Apollo 4, 5, and 6. There was no Apollo 2 or 3. The redesign was so extensive that NASA management decided to restart the numbering. Apollo 4, November 9, 1967, was the first all-up test of the giant Saturn V rocket. It was a complete success, validating the design of the launch vehicle and the new command module's heat shield at lunar return speeds. Apollo 5, January 22, 1968, was the first uncrewed test of the lunar module in Earth orbit. It tested the LM's descent and ascent engines, including a critical fire-in-the-hole abort test, where the ascent stage would fire while still attached to the descent stage. Despite a few computer issues, the mission proved the LM was ready to fly with a crew. Apollo 6, April 4, 1968, was the second Saturn V test flight, but this one encountered serious problems. The rocket experienced violent pogo oscillations, and 2 of the second stage engines shut down prematurely. Though the spacecraft was able to complete its mission, the issues showed the Saturn V still needed work. Despite these hiccups, NASA managers, confident the problems could be fixed, decided the next flight would be crewed. That next flight was Apollo 7, October 11, 1968. This was the first crewed Apollo mission, an Earth orbital flight, testing the completely redesigned command and service module. The crew of Wally Schirra, Don Isley, and Walter Cunningham spent 11 days in space, thoroughly checking out every system of the CSM. The mission was a spectacular success, but it was also tense. Schirra, a veteran of Mercury and Gemini, was fighting a cold and grew increasingly irritable with what the crew felt were excessive demands from mission control. Despite the friction, the spacecraft performed flawlessly. The United States was back in the crewed spaceflight business. Then came one of the most daring and decisive decisions of the entire space program. The CIA had intelligence that the Soviet Union was preparing a manned mission to loop around the moon. With the lunar module behind schedule, NASA managers made a bold call. Apollo 8 would not just test the CSM in Earth orbit. Instead, they would send it all the way to the moon. Apollo 8, December 21, 1968, was a monumental leap. Astronauts Frank Borman, James Lovell, and William Anders became the first humans to leave Earth's gravity, the first to see the far side of the moon with their own eyes, and the first to witness an Earthrise over the lunar horizon. On Christmas Eve, As their spacecraft orbited the moon, they took turns reading from the book of Genesis to a captivated global audience, a moment of profound beauty and reflection during a turbulent year. Apollo 8 was more than a mission. It was a testament to human courage and a pivotal moment that saw America seize the lead in the space race for good. The next two missions continued the careful, step-by-step testing. Apollo 9, March 13, 1969, was an Earth orbit mission that tested the complete Apollo spacecraft, the first flight of the full lunar module with a crew. For 10 days, astronauts Jim McDivitt, David Scott, and Rusty Schweickart practiced separating the LM from the CSM, flying the LM independently, and performing a critical spacewalk to test the lunar EVA suit and life support system. They successfully demonstrated all the steps of a lunar landing mission, except the landing itself. Then, Apollo 10, May 1826, 1969, was the final dress rehearsal. Tom Stafford, John Young, and Gene Cernan took the entire Apollo spacecraft to the moon. Stafford and Cernan flew the lunar module, nicknamed Snoopy, to within 50,000 feet of the lunar surface, a mere 9.4 miles, scouting the landing site in the Sea of Tranquility before returning to the CSM Charlie Brown. They tested the landing radar and practiced the descent profile, stopping just short of the final commitment to land. Everything was now ready. The next mission would attempt the real thing. The pressure on NASA and the crew of Apollo 11 was immense. The world was watching. President Kennedy's deadline was just 5 months away. The crew selected for this historic attempt was Neil Armstrong, the mission commander, Edwin "Buzz" Aldrin, the lunar module pilot, and Michael Collins, the command module pilot. After years of preparation, the Saturn V rocket carrying Apollo 11 lifted off from Launch Complex 39A at the Kennedy Space Center on July 16, 1969. Let's dive deep into those moments, uncovering the details that make this story so compelling. We'll explore the engineering marvels, the human emotions, and the split-second decisions that culminated in humanity's giant leap. The Saturn V rocket, standing taller than the Statue of Liberty, has indeed lifted off without a hitch. But what did it feel like to be inside that spacecraft, and what exactly was happening during those critical first moments? Let's start there. Imagine being Neil Armstrong, Michael Collins, or Buzz Aldrin, strapped into your couches inside the command module, which your crew has named Columbia. Beneath you is a rocket generating 7.5 million pounds of thrust, a force so immense it feels like a continuous earthquake. You're being pressed back into your seat by vibrations and noise, a deafening roar that you don't just hear, but feel in your very bones. The sky outside the small windows shifts from blue to black in mere minutes as you tear through the atmosphere. This launch was the culmination of a decade of work by over 400,000 people, and all that energy was focused on propelling you 3 forward. The journey to the moon isn't a straight shot. It's a series of carefully choreographed steps. The first is to get into a parking orbit around Earth. As the powerful first and second stages of the Saturn V burned out and fell away, the third stage, known as the SIVB, performed a critical job. It gave one final push to get Columbia and the attached lunar module Eagle into a stable temporary orbit about 115 miles above our planet. This is where the crew took a breather. For about an hour and a half, they circled the Earth, not as tourists, but as busy pilots, meticulously checking every system on their spacecraft to ensure everything was go for the next most crucial burn of their journey. That next maneuver is the Trans-Lunar Injection, or TLI. This is the moment they truly leave Earth behind. After their brief orbit, the engine on the SIVB third stage ignited again. It didn't just fire for a few seconds, it burned for a full 6 minutes, accelerating the spacecraft to a speed of over 24,000 miles per hour, which is fast enough to break free of Earth's gravity. Think of it like rolling a marble up the side of a large bowl. The TLI burn is the push that gets the marble to the very top of the bowl's edge. Once it's over that edge, it naturally coasts down the other side, pulled by the moon's gravity. At this point, the crew performed a beautiful and delicate maneuver. They separated the Command and Service Module Columbia from the now spent third stage. Then, Michael Collins, with the skill of a master pilot, turned Columbia around, flew it back to the top of the rocket stage, and gently docked with the lunar module Eagle, which had been stored inside the rocket during launch. Once securely connected, he pulled Eagle out, and the two spacecraft, now joined nose to nose, continued their coast toward the moon, leaving the Saturn V's third stage to drift away in space. For the next 3 days, they were coasting, but this wasn't a passive ride. They were constantly making small course corrections, monitoring their systems, and preparing for the lunar orbit insertion burn. The world outside their windows changed dramatically. The Earth shrunk to a beautiful blue and white marble, while the moon, which started as a distant crescent, grew larger and larger, its craters and seas becoming starkly visible, a constant reminder of their incredible destination. Now, let's set the scene for the drama of the landing. On July 20th, after successfully entering orbit around the moon, Neil and Buzz floated through the tunnel from the Command Module Columbia into the lunar module Eagle. Imagine putting on a bulky backpack and then trying to climb through the narrow opening between two cars of a moving train. Only this train is traveling at thousands of miles per hour in the vacuum of space. That was the transfer. Once inside the Eagle, they powered up its systems, said a temporary goodbye to Mike Collins, and undocked. As the spidery-looking Eagle separated from the sturdy Columbia, Mike Collins' voice came over the radio with a simple, poignant wish. "You guys take care." He would now orbit the moon alone, becoming what some have called the loneliest man in history, as for 48 minutes of every 2-hour orbit, he would fly behind the moon, completely cut off from all communication with Earth and his fellow astronauts. The descent began smoothly, but as you noted, it quickly became a high-stakes drama. The computer alarms that flashed were a 12:02 and then a 12:01 alarm. In the calm, technical language of the astronauts, they radioed, "Houston, we've got a 12:02 alarm." In the cockpit, however, their hearts must have been pounding. These were program alarms, indicating the computer was overloaded. It was trying to do too many things at once. A young guidance officer in Mission Control, Steve Bales, had to make a split-second decision. He'd seen this in a simulation and knew that while the computer was shedding less critical tasks, the essential functions for landing were still running. He gave the go to continue the descent. This was a moment of incredible trust in both the machine and the people on the ground. But the challenges weren't over. The automatic guidance system was indeed taking them directly into a crater the size of a football field, littered with car-sized boulders. Neil Armstrong, with the coolness of a test pilot, took manual control. He pitched the Eagle over to a more horizontal flight path, effectively flying it like a helicopter, skimming over the boulder field, his eyes darting between the window and the instruments, searching for a safe, clear spot to touch down. All the while, the fuel was dwindling. They had a low-level fuel call at 5% remaining. Buzz Aldrin began calling out the data like a metronome. "Forward, forward, good. 40 feet down 2.5, kicking up some dust. The tension in mission control was so thick you could cut it with a knife. The capsule communicator, Charlie Duke, later said his heart was thumping so hard he could feel it in his throat. When he called, 60 seconds, and then 30 seconds, it meant they had less than a minute's worth of fuel before they would have to abort, jettison the descent stage, and fire the ascent engine to crash back into orbit. But they were so close. Then, finally, the blue landing light lit up on the console, indicating contact with the lunar surface. That's when Neil's calm, iconic voice announced, "Houston, Tranquility Base here. The Eagle has landed." The relief was explosive. Charlie Duke, his voice cracking with the emotion of the moment, responded, "Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue." We're breathing again. After the landing, there was a planned rest period, but can you imagine trying to sleep after that? The adrenaline was still pumping. Instead, Neil and Buzz decided to move the historic moonwalk earlier. Preparing to go outside was a mission in itself. Putting on their portable life support systems, the large backpacks that provided their oxygen, temperature control, and power, was a complex ballet in the cramped cabin of the Eagle. Then they had to depressurize the cabin. When Neil Armstrong backed out of the hatch and started his slow, careful descent down the 9-rung ladder, a television camera, deployed by pulling a simple handle, sent those ghostly, flickering images back to Earth. An estimated 600 million people, 1/5 of all humanity at the time, were glued to their television sets, witnessing the impossible become real. When he reached the bottom, he paused and said those immortal, slightly debated words, "That's one small step for man, one giant leap for mankind." He intended to say, "for a man," which makes more grammatical sense, and most historians believe that's what he meant, though the A was lost in transmission. The important thing is the sentiment was perfectly clear to everyone watching. Buzz Aldrin joined him shortly after, describing the scene as magnificent desolation, a perfect, poetic summary of the beautiful, barren, and untouched landscape before them. For the next 2.5 hours, they were like children on the most incredible field trip imaginable. They bounced around in the moon's 1/6 gravity, a movement that became known as the bunny hop. They did more than just plant the American flag. They conducted science. They set up a device called a seismometer to listen for moonquakes, and a laser reflector that scientists still use today to measure the precise distance between the Earth and the Moon. They collected rocks and soil using tongs and a special scoop to gather 47.5 pounds of precious lunar material. And you mentioned the poignant artifacts they left. Along with the flag and the scientific gear, they left a silicon disc bearing goodwill messages from 73 world leaders, a gold olive branch pin as a symbol of peace, and a very special private memorial, a patch from the Apollo 1 mission, honoring their friends Gus Grissom, Ed White, and Roger Chaffee, who had perished in a launch pad fire 2 years earlier. This act connected their triumphant success directly to the sacrifice that made it possible. All the while, Michael Collins was orbiting 60 miles above them in the Columbia. He wasn't just waiting. He was a busy pilot and navigator, maintaining the spacecraft, making observations, and most importantly, preparing for the critical rendezvous. He later wrote that he was acutely aware of his solitude, but he was also deeply conscious of being a part of this great endeavor. He knew that if anything went wrong with the Eagle's ascent, he would have to return to Earth alone, becoming the only person in history to bring back the story of a tragedy he witnessed from orbit. After 21 hours and 36 minutes on the surface, the ascent stage of the Eagle fired its engine, lifting Neil and Buzz off the moon to a perfect rendezvous with Mike Collins in the Columbia. The docking was smooth. The astronauts and their precious moon rocks transferred back to the command module, and the Eagle was jettisoned, sent to eventually crash onto the lunar surface. The final leg of the journey home was a quiet and reflective time. They had done it. The engine on the service module fired to push them out of lunar orbit and onto a trajectory back to Earth. As they sped home, the planet of their birth grew larger in their windows. On July 24, 1969, they re-entered the Earth's atmosphere in a fiery blaze, protected by their heat shield, and splashed down safely in the Pacific Ocean, where the USS Hornet was waiting to recover them. President John F. Kennedy's audacious goal, set just 8 years earlier, had been achieved with 5 months to spare, a testament to human courage, ingenuity, and the power of a united effort. With the primary goal of the Apollo program accomplished, the focus shifted from just landing to conducting meaningful scientific exploration of the moon. The public's interest, however, began to wane. The subsequent Apollo missions, while less famous than Apollo 11, were in many ways far more ambitious and scientifically productive. Apollo 12, November 14th to 24th, 1969, demonstrated that a precision landing was possible. Commander Charles Pete Conrad and Alan Bean set their lunar module Intrepid down within walking distance of the Surveyor 3 probe, which had landed on the moon 2.5 years earlier. They collected parts of Surveyor to study the effects of long-term exposure to the lunar environment. Conrad and Bean conducted 2 moonwalks and deployed the first full Apollo Lunar Surface Experiments package, ALSEP, a suite of scientific instruments that would radio data back to Earth long after they departed. Then came Apollo 13, April 11th to 17, 1970. What was planned as the third landing mission suddenly became a fight for survival. 2 days into the mission, an explosion ripped through the service module, crippling the spacecraft. The famous words spoken to Mission Control were, "Houston, we've had a problem." With the command module losing power and oxygen, the crew, Jim Lovell, Jack Swigert, and Fred Hayes, retreated into the lunar module Aquarius, using it as an unplanned lifeboat. In a gripping real-time drama, engineers on the ground and the astronauts in space worked together to improvise solutions for carbon dioxide scrubbers, power conservation, and a safe trajectory around the moon and back to Earth. The world watched and held its breath. The successful splashdown of Apollo 13 was, in the words of many, NASA's finest hour. It was a failure of the mission that became a triumph of human ingenuity and courage. Shaken but undeterred, NASA made extensive modifications to the spacecraft and pressed on. Apollo 14, January 31st, February 9th, 1971, saw Alan Shepard, America's first man in space, finally get his chance to walk on the moon. Along with Edgar Mitchell, Shepard explored the Fra Mauro Highlands, originally the target for Apollo 13. On his second moonwalk, Shepard famously pulled out a makeshift golf club head attached to a lunar sample handle and hit 2 golf balls, declaring the second went miles and miles and miles in the low lunar gravity. The final 3 missions, Apollo 15, 16, and 17, were the J-series missions, featuring major upgrades. They carried more supplies for longer stays, more sophisticated scientific instruments, and a revolutionary new vehicle, the Lunar Roving Vehicle, or Moon Buggy. This electric car dramatically expanded the range of the astronauts' exploration. Apollo 15, July 26th, August 7th, 1971, with David Scott and James Irwin, landed in the spectacular Hadley Rille area at the base of the lunar Apennine Mountains. They were the first to use the rover, driving over 17 miles and discovering the Genesis Rock, a piece of the moon's primordial crust. Apollo 16, April 16 to 27, 1972, was the first and only mission to land in the lunar highlands. John Young and Charles Duke explored the Descartes region, collecting samples that helped scientists understand the volcanic history of the moon. The grand finale was Apollo 17, December 7th and 19th, 1972. This mission broke many records: the longest lunar landing, the longest total moonwalks, and the largest sample return. It was also the first to include a scientist-astronaut, geologist Harrison Jack Schmitt. He and veteran astronaut Gene Cernan explored the Taurus-Littrow Valley, a geologically rich area with mountains and a dark, flat floor. Before departing, Cernan spoke these poignant words: "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." As of today, Eugene Cernan remains the last human to have walked on the moon. The Apollo program was far more than a political stunt. It was one of the greatest scientific endeavors of the 20th century. The 842 pounds, 382 kilograms of lunar rocks and soil returned by the Apollo astronauts have revolutionized our understanding of the moon, the Earth, and the inner solar system. Here are some of the most profound discoveries. First, we learned that the moon is not a primordial object. It is an evolved, rocky body, much like Earth, with a complex geological history involving volcanism and massive impacts. It has a layered structure with a crust, mantle, and core, though its core is much smaller relative to its size than Earth's. Second, the moon is ancient, and its surface preserves a record of the first billion years of solar system history, a record largely erased on Earth by erosion and plate tectonics. By dating the Apollo samples, scientists determined that the oldest moon rocks are about 4.46 billion years old, even older than the oldest rocks found on Earth. The moon itself formed about 4.5 billion years ago. Third, the moon and Earth are genetically related. The most widely accepted theory today, the giant impact hypothesis, was strengthened by Apollo data. It posits that early in Earth's history, a Mars-sized body nicknamed Theia collided with the proto-Earth. The debris from this cataclysmic impact coalesced in orbit to form our moon. This explains why moon rocks have oxygen isotope compositions nearly identical to Earth's, yet are depleted in volatile, easily vaporized elements and iron. The impact would have vaporized the lighter elements and blasted the material that formed the moon from the Earth's mantle and the impactor. Fourth, the Apollo missions taught us that the moon is utterly lifeless. No living organisms, fossils, or native organic compounds were found. It is a sterile world. Fifth, we learned about the moon's dramatic early history. Early in its life, the moon was likely molten to a great depth, forming a magma ocean. The light, crystalline rock anorthosite floated to the top to form the ancient highlands, while the denser minerals sank. This was followed by a period of intense bombardment by asteroids, which created the giant basins that were later filled by dark lava flows between 3.2 and 4 billion years ago to form the Maria, or seas, we see today. These discoveries didn't just tell us about the moon. By understanding the moon's cratering history, scientists were able to calibrate a geological timescale for cratering across the entire inner solar system, helping us date surfaces on Mercury, Venus, and Mars. The Apollo program gave us a new perspective on our own planet as well. The iconic Earthrise photos from Apollo 8, showing our beautiful, fragile-looking blue marble hanging in the blackness of space, became a powerful symbol for the environmental movement, emphasizing the unity and fragility of our home world. The Apollo program's legacy isn't confined to space. The enormous technological challenge of going to the moon forced innovations that have since filtered down into countless aspects of our daily lives. These are called spin-offs. Here are just a few examples. Integrated circuits. The Apollo guidance computer was one of the first major users of integrated circuits, or microchips. The need for small, lightweight, and reliable computing for Apollo helped kickstart the entire microelectronics revolution that led to modern computers and smartphones. Cordless tools. To build tools for taking core samples on the moon, Black Decker, in partnership with NASA, developed a compact, self-contained, battery-powered drill. This technology directly led to the creation of the cordless vacuum cleaners, power drills, and other cordless tools we use every day. Medical imaging. Digital image processing techniques developed to enhance pictures of the moon were later adapted for use in CAT scanners and MRI machines, revolutionizing medical diagnostics. Water purification. NASA developed electrolytic silver iodizer technology to purify drinking water on the Apollo spacecraft. This same technology is now widely used to kill bacteria in municipal water systems and cooling towers. Thermal protection. The reflective insulation used on the Apollo spacecraft to protect it from solar radiation is now used worldwide in everything from home insulation, like mylar-based materials, to emergency blankets that marathon runners use after a race. Scratch-resistant lenses. The plastic lenses in astronaut helmets needed to be protected from abrasive lunar dust. A company developed a special scratch-resistant coating for them, a technology that was later applied to eyeglasses and sunglasses, making them far more durable. Food safety. NASA's work in developing the Hazard Analysis and Critical Control Point HACCP system to ensure food safety for astronauts was adopted by the food industry and is now used globally to keep our food supplies safe. This list goes on, touching fields from athletics footwear to firefighting equipment. The investment in Apollo, therefore, wasn't just about exploring space. It was an investment in technological innovation that has paid dividends for decades in our economy and our quality of life. A project of Apollo's scale, of course, came with a staggering price tag. So how much did it cost? The total amount spent on Project Apollo between 1960 and 1973 was $25.8 billion, and in 2020 dollars, that's approximately $257 billion. If you include the related projects that enabled Apollo, like Project Gemini and the Robotic Lunar Program, the total cost of the American lunar effort rises to about $28 billion in then-year dollars, or $280 billion adjusted. To put this in perspective, at its peak in 1966, NASA's budget consumed about 4.4% of the entire federal budget. It was a massive national commitment, employing hundreds of thousands of people and involving thousands of companies. The spending peaked in 1966, 3 years before the first landing, as the heavy research and development work was completed. Why did it end? After Apollo 17, there were originally plans for missions through Apollo 20. However, budget cuts, shifting national priorities, like the Vietnam War and the War on Poverty, and a decline in public interest after the initial landing led to the cancellation of these final missions. The Apollo hardware that remained was used for the Skylab space station and the Apollo-Soyuz test project, a joint docking mission with the Soviet Union in 1975 that marked the end of the Apollo era. So, we've turned over every stone. We've followed the Apollo program from its origins in Cold War tension to its conclusion with the final footsteps on the moon. We've met the people, understood the machines, mourned the tragedies, and celebrated the triumphs. We've seen how it expanded the frontiers of science and how its technology reshaped our world. The Apollo program was a testament to what humanity can achieve when we dare to dream big, when we focus our intellect and resources on a goal that seems just beyond our reach. It showed us that the greatest challenges bring out the best in us: ingenuity, courage, cooperation, and perseverance. The footprints left on the moon by 12 Americans are not just marks in the dust. They are a permanent message to the future, a promise of what is possible. They remind us that our horizons are not limited by our atmosphere, that our future as a species does not have to be confined to this single world. The story of Apollo is not just a history lesson. It is a source of inspiration, a benchmark of human potential, and a prologue to the future. As we today look again to the moon with the Artemis program, aiming to send a new generation of explorers, including the first woman and the first person of color, to the lunar surface, we stand on the shoulders of the Apollo giants. Their story, the complete story of how we went to the moon, is a story that deserves to be told and retold. For in understanding how we did it then, we find the courage and the blueprint for where we will go next, back to the moon and on to Mars and beyond. And so, there you have it, the story of how 3 human beings, supported by the work and the hope of hundreds of thousands more, ventured into the absolute unknown, touched the face of another world, and returned home to tell the tale. It's a story that never gets old, does it? Every time you hear about that small step, that giant leap, it sparks something inside us, a sense of wonder, a feeling of incredible possibility. It's a reminder of what we are capable of when we dare to dream big, when we combine our curiosity with our courage, and when we work together toward a goal that is greater than any one of us. Those boot prints are still there, you know, up on the moon in the fine gray dust of the Sea of Tranquility, perfectly preserved in the airless silence. They are a permanent message, etched into the lunar soil, a testament to a time when we, as a species, reached for the stars and actually grasped one. But the story isn't just a memory, it's a prologue. The spirit of Apollo didn't splash down in the Pacific Ocean and end there. It lives on in every rocket that launches to the International Space Station, in every rover trundling across the landscape of Mars, and in every telescope that peers back to the dawn of time. The knowledge we gained, the technology we invented, and the courage we found is the inheritance we are building upon today. Right now, a new generation is looking up at that same moon. New spacecraft are being built, new missions are being planned, and the goal is no longer just to visit, but to stay, to build, to learn, and to use our celestial neighbor as a stepping stone to the rest of the solar system. The journey that began with Apollo is far from over. In many ways, it's just beginning. So, the next time you're outside on a clear night and you see the moon hanging there, bright and silent, I want you to look at it a little differently. Don't just see a distant rock. See a destination. See a place where we left our mark. See a world of future cities and new adventures. Remember the courage of Armstrong, Aldrin, and Collins, and the thousands of people who got them there. Let it remind you that no challenge is too great, no goal is too far, and that the human spirit, when it sets its mind to something, is truly and utterly unstoppable. Thank you for joining me on this incredible journey through history. If you enjoyed this deep dive into the Apollo program, make sure to subscribe to the channel and hit that bell icon so you don't miss our next adventure. Until next time, keep looking up. Good night. Have a deep, calm sleep.